Okay, now you should hear me. Okay, so welcome to the amphitheater and welcome to Eva Schinnerer, who we have the pleasure to have today for a seminar. So I would like to introduce briefly Eva, if that is necessary, I don't know. So first of all, it's my great pleasure to welcome you. And Eva is today a staff scientist at the Max-Planck-Institut for Astronomy in Heidelberg. And she's also an adjunct associate astronomer at the National Radio Astronomy Observatory in the US since 2011. So she thesis in 1999 on a topic nuclear dynamics and star formation in two representations.
S'il y avait un problème de bouclage des boucles.
Quel compilateur?
Ben, j'en sais rien.
Ah,
spécialiste. Et puis alors, c'est l'université de Nice, c'est pas l'observatoire, c'est l'université, donc c'est un vaste truc de trouver le service informatique, trouver les...
Any questions?
Avec le service informatique.
Mais soit c'est du GeFortran, Trans, soit c'est du iFort. Mais
ben, ici, moi, j'utilise iFort. Et...
Okay, good. That's very pleasant. So under the supervision of Reinhard Genzel, I think, and thereafter she was a postdoc at Caltech and then a Jansky Fellow at Socorro at the NRO. So her interests are very vast and encompass quite a number of topics from the star formation through cosmic times, the evolution of AGNs, the state and dynamics of the interstellar medium, and all subjects that she explores basically with facilities like, the best interferometers in the world, so the VLA, NOEMA, and ALMA, of course. She has been very productive. She published about more than 400 papers, I think 412, I checked this morning, refereed papers and many other papers as well. And not only that, but she has has a lot of numerous students over the last decades and from like a new generation of people working in that field. She has also been part of a number of successful and trailblazing large projects and programs with very nice names. And so just to name a few, it's PAUS, Kingfish, the VLA Cosmos, and PHANGS. And I think today you will present some of the quite spectacular results and recent results of PHANGS. So again, many thanks for coming to Paris to give this talk. I'm happy to see there are many people in the amphitheater, and I'm sorry for the little bit of a chaotic start with the organization. And now the floor is yours, Eva, and thank you again.
Thank you very much for a nice introduction words. Also, thank you very much for giving me the opportunity to present you some of the latest results from the PHANGS collaboration, and also for inviting me to visit Paris. So today I would like to talk about what we've learned over the past few years on the cloud scale view of the star formation process. And in particular, I will be focusing on the PHANGS collaboration and their results. Okay, so but first it would be good to understand why we want to have a look at the cloud scale view on the star formation process. And this basically relates to which physical processes control the formation of stars. So star formation, basically you can think about there are three main categories of processes that control it. There's gravity or the self-gravity, causing, of course, the gas to condense from stars. It's turbulence, either on small scales injected by stellar feedback, or also on large scales like the gas flows that happen in galaxies. And then, of course, there's the various forms of radiation emitted by the stars and impacting the process. On the scales where you can study star formation, they basically range from megaparsecs, where you study full galaxy populations, to looking into what happening processes going on in galaxies on kiloparsec scales. If you zoom further down, you're happening to see individual star clusters of their formation on the scales of parsecs till you end up with a single star. So the other thing to consider is also how is process the cycling of the gas from the intergalactic medium onto a galaxy. There in the galaxy, you have gas flows that are redistributing this gas. You have to consider the history of the star formation in galaxies by looking at the stellar populations, what happens. You have metal enrichment due to the formation of stars. You have galactic structures, spiral arms, bars, and so on. And of course, in there, the star formation is one aspect to study. It's basically also can be considered as a baryon cycle that happens within the galaxy. Then you can go to the nuclears. There you have nuclear clusters, supermassive black holes. They might eject outflows, going back and bringing the gas back to the halo or also the intergalactic medium. And again, for the talk here, I would like to focus on basically the star formation and the baryon life cycle. And again, on these different scales, you can learn different aspects related to the star formation process. Galaxy populations give you global properties to understand how different galaxies have star formation. If you want to understand galactic environments or look at that, you understand the local properties or processes that might set the conditions for star formation. If you go to star clusters, you can start to look at very detailed physics and also the microphysics of the star formation process. So again, for this talk, I'd like to focus on basically if there are local conditions, if they vary across galaxies, and potentially what is the impact for the star formation we see. So coming to the baryon life cycle or star formation life cycle, so what you can take from basically in the left-hand side of the image or from here. You take like a parcel out of galaxy, let's say it's about a few 500 parsecs across. You will find components like the diffuse atomic gas that starts to kind of become more dense and become molecular. At some point, this molecular gas can start to become self-gravitating and collapse, where you start to have stars and star clusters being formed and born. These clusters, again, during their formation, they inject stellar winds and supernovae, so they cause H2 regions and ejector and cause the molecular gas reservoir basically to either be consumed or also basically dissociated, becoming more in the ionized gas phase. And after this process has settled for a while, this basically ionized gas can start to cool, become diffuse and atomic, and you're starting this life cycle again. As you see on the bottom here, in order to cover this process, you need to go cover basically the full electromagnetic wavelength spectrum to capture all the different processes that are available. And during the next minutes, I'd like to focus basically on the conversion of molecular gas to stars, and then also the impact of feedback. In particular, the questions that are important in this respect is where, when, and how do stars form? How efficient is star formation? And also if it is the same everywhere. And how long does it take to form a star? How long can it proceed? And also what shuts off star formation in different parts of galaxies or in different galaxies. So the first thing to consider when addressing this question is the question to ask you, where do I want to study it and how do I want to study it? Cloud scale resolution basically now revealed that the spiral arms are no longer smooth. They have intrinsic structures, and also that there is abundant emission between the arms in the interarm region. And this basically showed you that it is a lot of information gained by this change in resolution and keeping the sensitivity. So the revolution with ALMA is the picture on the right-hand side I'm showing you, which is still state of the art, took about 200 hours of plateau de Beer time. And now with ALMA, you can obtain a similar image taking about 1 or 2 hours with the 12-meter main array. So basically ALMA now allows us to do this in a more survey efficient mode, collecting samples. The other reason why this is interesting, so what you're seeing here is basically stellar light from the underlying population, together in the orange showing the H-alpha emissions, so where H2 regions are sitting. And when you now pair this with ALMA, similar having now resolution similar to the ground-based seeing you're achieving, you're seeing now that you can basically look at the relation that the molecular gas has to the ongoing star formation to the stellar structure. So where to study? Basically, we know for almost 2 decades that if you look at the global star formation rate versus the global molecular gas mass of galaxies that form stars form a very tight sequence that is called the main sequence of star forming galaxies, adopted a couple of years later. So that means most of the stars are born in galaxies in this kind of mass range here. And if you choose a slightly different representation where you look at the star formation rate density per stellar mass, per cosmic volume, you basically see what you see here as a function of stellar mass, and color-coded are different redshifts regimes, is that the typical, most stars always born in the same kind of galaxies. So it's galaxies around with stellar masses like our own Milky Way, and that this hasn't evolved very much through cosmic time. So even looking at galaxies today will help us understand how potentially star formation has proceeded also in the earlier universe. So basically with that in mind, we started PHANGS, which stands for Physics at High Angular Resolution in Nearby Galaxies. And the aim is to understand the interplay between the small scale physics of gas and star formation with galactic structure, but also linking it back to galaxy evolution. For that, we decided to have a modern, more cosmological looking facing sample that is sampling the main sequence in the very local universe. So we set our distance requirements to about 17 megaparsecs, so that 1 arc second, which is typical seeing, is about 100 parsec. So we can basically probe the star forming units like giant molecular clouds or H2 regions. Galaxies shouldn't be too inclined and accessible from the west with ALMA. So and this is the sample selection. This is the team, I think almost complete. On the top, you saw the people who started this effort some 6-7 years ago. And I'm particularly thankful to Guillermo Blanc, Eric Amselem, and Adam Leroy, who I could convince to basically start this effort and build up this collaboration from scratch. So the one thing to say, I'll say that later. So this is now the ALMA resolution I was talking about. So you're seeing here pictures of 90 nearby galaxies at a resolution of about 100 parsecs or so. And they are basically color-coded and sorted from, on the top right, from galaxies that have very strong spiral arms to multi-arms in the molecular gas to no spiral arms, and a set of galaxies that we weren't able to visually classify or achieve agreement among the 10 of us who attempted to do that. And here, if you see a zoom in, you can just really appreciate this large variety in molecular gas morphology, which basically also then tells us that there must potentially be an effect on how star formation proceeds, and that might proceed differently in these types of galaxies. So these molecular gas observations are paired with observations of H2 regions plus the underlying stellar potential using MUSE, and also HST observations from stellar clusters. So these are 3 large or treasury programs that form the foundation of this collaboration or the analysis. And this isn't all, we have more data, and basically that's what sets this collaboration apart. We started with basically not much observations, and we said we wanted to build up this really panchromatic database that will help allow us studying star formation and other aspects related to how the local galaxies came into place. So there's 90 galaxies of ALMA. They are paired with ground-based H-alpha imaging. A subset of them have HST observations, and also we are collecting far UV observations with the AstroSat satellite. This is then combined with MUSE for even smaller subset, and hopefully starting end of June with also JWST incoming near-infrared and mid-infrared imaging. As well, there are efforts to have compared but lower resolution emission at the atomic gas, which is another important component, but which I will ignore. One reason is the resolution is lower and the sample coverage is not as good. So just, I told you the ALMA galaxies, this is a subset of the Muse galaxies, and the colors are set the same. So you really appreciate that these galaxies, some are younger, being more blue, some are older, some have more structure or dust extinction across them. And the one thing that is kind of amazing about PHANGS is if you look at the left-hand panel, it shows you the number of spatial resolution elements, so that are basically independent given the scene, versus the number of the spatial resolution, and you clearly see that PHANGS stands out. So we have more individual spectra than the SDSS. Of course, there's a caveat: if you look at two neighboring regions in a galaxy disk, they might be sharing exactly the same properties. But also this gives you an idea that PHANGS is covering a very different phase space in this IFU surveys. And this just shows you the distribution of the ionized gas. So everything in red is H alpha. So these are the star forming H2 regions. And this is the last. So these are the HST images. They are published as part of the ESA Hubble information, and looking at them, you already see that there's a lot of information to be gained from the structure, but as well as clusters. And this also shows you that basically PHANGS compared to the Legacy survey, who's targeting a much wider range, but also many more low mass galaxies than PHANGS, and also compared to the GOAL survey shown in red, there we see much that is basically focusing on the star bursting galaxies, so that this fills in a gap in our knowledge. So now I would like to switch to results, and as I said, I'll be having a very PHANGS biased view and giving you basically some of the information we learned about the last years. So basically what I want you to take away from this part of the talk is that the gas structure is set by a balance of the internal and the external pressure, and that local and our galaxy properties do matter. So for the context of the next few minutes, just remember the line width we observe in CO is a measure of the internal turbulence, which then you can take as a proxy of the kinetic energy. And similarly, the gas surface density can be seen as a proxy for mass, and that is a proxy for potential energy. So this was a paper using only a first subset of the galaxies we had, and you see on the y-axis the line velocity plotted on the x-axis against the gas surface density, and you see that these form a fairly linear or tight relation. And despite the fact that the range in gas surface density that we cover is like 4 orders or 3 orders of magnitude. And that basically tells you that the gas is kind of in energy equipartition, so that it is the same. And the interesting bit is also that you compare it with something shown in orange, like the antennae, which is a nearby merger, that those are the same conditions everywhere. And the conclusion, which wasn't totally new, is that basically that the internal pressure in the cloud is similar to the external pressure in the cloud. So a couple years later, with the full sample, Jai Sun revisited this information. And what you're seeing here now is an approach where we took the measurement of the internal pressure on a scale of 120 parsec, averaged in an aperture of 1 kiloparsec, versus the external pressure, so mostly hydrostatic pressure, measured on 1 kiloparsec. And so what you see here is a very tight relation. However, if you look in the bottom panel, you see based on the ratio that the clouds appear overpressurized, so they kind of should expand. And since we know they're not expanding, they are forming stars, so they must collapse. The question was, have we missed a component to do that? And it became clear that we also need to take the self-gravity of the clouds themselves into account when we are calculating the dynamical equilibrium pressure or the external pressure. And that basically then, once you do that, you see that the clouds are, the internal and external pressure are in balance, and basically that there is another component to take into account. Then there was a question, are the gas properties as we can observe them, are they the same across the galaxies, or do we see variations? And here you see the plot of global star formation rate versus global stellar mass. And the color coding is by the average gas surface density as measured on 150 parsec. And the darker the clouds, the points are getting, the higher is the gas surface density, which basically increases to higher stellar masses. And also maybe there's a trend that you have higher gas surface densities for higher star formation rates. So there seems to be some fact. There's also a different way to look at the gas properties. This is trying to break them up into individual clouds. And this is a measurement for 5,000 clouds in 10 galaxies, all looking at the same data at 90 parsec resolution, having the same spectral resolution, having the same noise signatures. So everything is exactly the same. And what you see here is that there are variations in the classical parameters where you describe the gas properties, the viral parameter, the gas surface density, line width, as well as internal pressure. So there is from different lines, there is evidence that the gas properties as we by measurement in CO are varying. This also then becomes interesting when you look not only varying between galaxies, but also within galaxies. So this is now measurements from about 60 galaxies. There you look at the line width versus the gas surface density. And in blue color codes, you're seeing the gas that is sitting in centers. And in red is the gas emission that you see in red, you see what gas emission that is sitting in centers, and in blue that are sitting in disk. And it becomes apparent that in galaxy centers, gas densities are not only higher, they also are more turbulent. And the question is, what is causing that? I'm sure François has a number of ideas. And the other aspect that was very interesting to look, if you look at the gas surface density as a function of radius, but you split your environment into if the gas is sitting in a spiral arm or in interarm. And while the scatter is very large, there is a small distinct difference, which is also a big question about what is the importance of spiral arms for the star formation process. So at least there seems to be an impact on the gas surface density we observe. So this Joy has pushed this, so this is the final bit of the analysis, to look at a number of properties to do this systematic search, and there is a lot of information. This paper is currently under review, so I expect this to be on AstroPH soon. So he looked at the molecular gas properties at 150 parsec, and he searched for correlations, anti-correlations of these molecular gas properties like the mass, radius, line width, pressure, viral parameter, as a function of local environment conditions. So these are the first few parameters, and also global galaxy properties. And the redder the boxes are, the higher the correlation is, and the darker blue the boxes are, the higher the anti-correlation is. And the thing that becomes very immediate at, just look at this table is that in general, local environment seems to have a stronger correlation than global galaxy properties. And on the bottom, you're seeing how these different quantities might be intercorrelated with each other. So the one thing I want you to take away from this plot is that it seems very clear that local environment seems to be more important than global galaxy properties. And this immediately leads to the speculation that the galaxy to galaxy scatter that we are seeing might be driven in the variations that the number of local environments that are present in different types of galaxies. So I hope this is basically what I wanted to say on this aspect, that you keep in mind molecular gas is in a fine balance. And also that there is now becoming more strong indications that it's the properties that are, that it's the conditions that are present in galaxies are driving the conditions for star formation rather than the galaxy as such. So the next aspect I'd like to cover is talk about star formation, and that's basically to take away that the efficiency of clouds to form stars varies across galaxy disks, but that stars, if they form, it happens very quickly. So this was a very simple experiment we wanted to do. So we took our maps of molecular gas and compared them to maps of H-alpha emission, where we basically made sure that the emission is mostly tracing H2 regions. And then we ask a very simple question: which sidelines contain molecular gas only, which sidelines contain molecular gas and star formation, and which sidelines contain star formation. There's a number of caveats in this kind of analysis, but it's a very simple question to do. We tried to have basically the same sensitivity cut on the molecular gas. It wasn't so easy to impose the same criterion on the star formation rate tracer for various aspects. But this is an example for 4 galaxies, and we look basically how the distribution in the total number of pixels with emission varies if we go from 140 parsecs up to 1.5 kiloparsecs. And the thing that becomes very clear that at the very highest resolution, you see a lot of non-forming gas, given our sensitivity to the massive star formation, that this is typically most abundant in galaxies, at least number of sidelines and the flux. And in order to basically start to see it, you really need to reach higher resolution below 0.5 kiloparsec, which was the best studies, the best resolution of a lot of studies looking into this topic. Jean Pan has recently followed up on that using the full ALMA sample and going for a fixed resolution of 150 parsec. And what you're seeing here from left to right, so in blue, is how the only molecular, the gas only sidelines increase as a function of stellar mass. So the different color coding going from light to dark colors tells you going from low mass galaxies to high mass galaxies, relatively speaking, in our sample. So this rising trend with more non-star forming or quiescent gas in massive galaxies basically is also accompanied by a low fraction in the star formation rate only sites. Surprisingly, the fraction of overlap regions is staying the same, so the number of star forming gas is the same across all the galaxies. So taking this star forming gas and see, we checked if there are any trends with Hubble sequence or basically across the main sequence of galaxies. And as you can see here, it's a scatter plot and there's no trend with colors. This slightly there changes if you go to the quiescent gas fraction. Their early type galaxies appear to have a very high CO only, gas fractions compared to the very late type galaxies. We seem to have a very low. If you're curious, I'm happy to talk more about this, but there's no trend with main sequence. So there are conditions for star formation are varying. Another thing to look at is basically looking at the time scale. So if you think about the baryon cycle, you can say there's phase, there are only CO, then I have star formation and CO happening at the same time, and then I only have star formation. And basically by combining these time scales, how long I do expect to see CO and how long do I expect to see my star formation rate tracer, I can get a fraction how long things happen. And this is basically what this plot shows. It's the 3 panels show different galaxies with different top mass. And if you focus on the really dark gray point, you see that the scaling factor is basically constant in all galaxies and constant as a function of radius. However, as you start to increase the resolution with which you look at it, and now if you focus on the magenta points, you start to see that the low mass galaxies seem to be much more efficient in forming stars compared to the high mass galaxies, and also that there's a radial trend with centers always being less efficient than outer disks. And in order to kind of see these differences, one needs to basically go below 300 parsecs so that you resolve the scale between these different units so that you really see the separations and get a handle on the time evolution. Another way, since I said galaxies have structures, contain spiral arms and bars, is to basically understand how's the distribution of molecular gas and star formation in these different components. So we basically generated environmental masks. This work was done by Miguel Carreta. And this is based on the S4G survey, who did a lot of work on characterizing galaxies and their structures. And the interesting thing, what you now see is our distribution in the area. So centers are forming a really small area shown in red on the top in area. However, they are really abundant in containing molecular gas mass as well as the star formation rate. And similarly, bars and spiral arms are much more prominent in the prominent when you look at their contribution to the molecular gas and the star formation rate compared to the area they cover. Another way to look at is basically what is the typical molecular gas surface density shown on the left in these different types of environments. And it's very clear centers have really high star formation molecular gas surface densities, but there are also these small variations between bar spirals and arms or disk, interarm or disk region. This persists also in the star formation rate surface density. And the interesting thing is now looking at the ratio of the two, which is the depletion time, which is shown in the right-hand side. And there, basically, the depletion time in the center seem to be very similar on average what you see in these other environments. However, the distributions are still distinctly different. And one other way to basically see, to understand better how much the ratio, how much the center's depletion time in the center might vary to the one in the disk. We looked at the ratios of these two for the barred galaxies shown in the green on the left and the unbarred galaxies. And one that becomes immediate is that while the average change in depletion time, the centers being more efficient changes, the one is the same between barred and unbarred galaxies, sorry. Barred galaxies have a much wider distribution. So that really tells us that centers of barred galaxies, there must be a number of physics going on. Another aspect is looking at the star formation scaling relations, and I introduced you already to the first one. And basically, you're using three observables to describe the star formation process in galaxies. That is stellar mass, star formation rate, and molecular gas. And the first one, star formation rate versus stellar mass, is a so-called star forming main sequence. People know for a long time. The second one is even older. It's the star formation rate versus molecular gas mass, also known as the Kennicutt-Schmidt. And the third scanning relation is molecular gas mass versus stellar mass. And while people have looked at that ratio, I think the term molecular gas main sequence has become popular in the past few years. And these three observables are basically combined, either using their global total masses or looking at surface densities, and there are a standard tool going from high redshift down to the most local galaxies. And so since we have exquisite observations of the star formation rates from the optical IFU, where we basically take H alpha and correct it for the dust attenuation, as well as the star formation, as well as the stellar mass from doing some full spectral fitting. And we can combine it with the ALMA data. We can also look how if these relations still persist at 100 parsec, what you see on the right, at 500 parsec and 1 kiloparsec. So how they involve in our data set. And here you see a list, apologies, numbers might be a bit small, of measurements that have been done, result measurements in nearby galaxies or local galaxies. And you see that the numbers are typically roughly the same. And the thing that we found most amazing is first that these scaling relations were still recoverable at 100 parsec. We kind of had expected that there might be only scatter plots because you're basically resolving the time evolution. Therefore, sorry, any potential relation might have vanished. Also, the values from the slopes we are deriving for the star formation main sequence on the left and the Kennicutt-Schmidt in the middle are similar and consistent with what people have derived in the literature at lower resolution, but it's not for the star formation molecular gas mass versus stellar mass. And one reason is how do you account for non-detections? And that kind of explains the differences we are seeing. The thing we now can do, we can also look at these at variations from galaxy to galaxy. So in the middle, you see the average from determining these scaling relations in all galaxies, and then each colored point is another galaxy. And so the color tells you the stellar mass, and the symbol size tells you the amount of star formation, global star formation rate. And what you're seeing is basically a scatter plot in symbol size as well as colors. Interesting is that the scatter is the smallest if you look at the Kennicutt-Schmidt across the galaxies. And so this kind of should imply that the star formation process itself might be more homogeneous. But we were in that paper speculating that the gas properties depend on the stellar potential. A more interesting aspect of this paper, led by Ismail Pessa, was basically to look how these scaling relations vary as a function of environment. So our spiral arms, centers, bars, and so on. So the different colors show you the different environments. On top, you're seeing the scaling relations in the different colors. On the bottom is our attempt to quantify basically variations. So alpha is the slope of the scaling relations, and the y-axis shows the offset relative to the dashed line, which in the top plot, which defines the global relation. And so what you see is that basically spiral arms in light blue are always on top of the relations, that the disks in purple basically define the relations, and that bars are typically below, and centers are more divergent, particularly if you look in the plots. So there are clear differences in these environments. Lastly, the question that has always been asked, particularly for simulations, is how efficient is the star formation per freefall time? And that is basically, you take the freefall time within a cloud, and you know the star formation in that entity and the cloud mass. So if you combine it, and from theory, if you average across the full population in a cloud, you expect a very low star formation efficiency of about 1%. So Diaz Utomo used our preliminary data set back in 2018 to look into this. So on top, you see various ranges derived in basically the Milky Way and also M51. And in the bottom, you see the distribution for the star formation efficiency, and the gray line shows you the 1% you expect, and it's very close. And on the right-hand side, you see basically how much these values change. This value change if you change the assumptions you're making. So this measurement seems robust and tells us that the overall star formation across galactic disks is inefficient, which is consistent again with also the finding that there seems to be a lot of gas, despite maybe at lower surface density that is not star forming. So to wrap up this part is basically that the efficiency of how clouds form stars in galaxies is varying, that stars form fast, but globally speaking, the conversion of gas into stars in galaxies is happening on a low path. So the last aspect I want to cover is stellar feedback. And I think there's now emerging that pre-supernova processes are important in disrupting the gas reservoir, and the role of the supernovae, who were traditionally seen as those are basically stopping star formation, is less clear. So one way to get at this is using this principle. There you look at gas peaks shown in orange and stellar peaks shown in blue. And you're asking how much on the gas peaks, how much star formation I can find, and the other way. And you basically get this kind of tuning fork diagram. And you look at this, and while you're increasing the aperture from very small apertures up to large, till you get basically the galactic average, which is the typical gas depletion time of about a gigayear or so. So this idea was applied by Melanie Chavance on a first subset, and they is making assumption on how long H-alpha emission is visible. They can determine that the molecular cloud lifetimes are very short, of about 10 to 30 megayears. That varies, and that the clouds have a long time, they are not apparently forming stars. There's the feedback time scale is very short, 1 to 3 megayears. And that basically has to point to pre-supernova feedback, because supernovae are expected to become very powerful only after about 5 megayears. So this initial study has now been extended to the full sample by Jaeon Kim. And here you see that basically the picture I showed you before, the distribution is roughly the same. The one thing that is now interesting, you could ask, how long is this cloud lifetime? Is that a function of galaxy properties? So now you see here the global star formation rate plotted against the stellar mass, color-coded by the inferred cloud lifetimes. And there's a trend that more massive galaxies appear to have longer cloud lifetimes compared to others. And Some of this trend is probably related to the fact that the fraction of CO dark gas is probably higher in low mass galaxies. So there's more things we have to learn and understand also about our tracers we are using. Coming back to the role and importance of pre-supernova feedback. So these are now the feedback times determined from a plot I just showed you a second ago versus global stellar mass, gas phase metallicity, as well as the average surface density of the molecular gas on GMC scales. And the thing that is interesting is that the feedback timescale shows a strong function of stellar mass, but basically no trend with metallicity or the gas mass surface densities. Another important result from Melanie's paper is basically if you look at the feedback timescales as a function of radius, I show it here for 3 of her 9 galaxies. And in black, you see basically her measured inferred feedback timescale, and in blue, different curves making assumptions about what is the typical timescale for supernovae, which are shown in the dotted line, photoionization, stellar winds, radiation pressure, and then combining all mechanisms. So if you combine all mechanisms, that is the blue shaded area, you see that it typically lies below the inferred feedback timescale, which is good because it means the mechanisms we think are doing the feedback are indeed can do it. But one thing to highlight is basically that the dotted line of supernovae is always significantly longer than what is measured. So basically it tells us that supernovae should not play a critical role in the destruction of the initial destruction of molecular gas. So another short digression on pre-supernova feedback and how it is. Ashley Barnes took the Muse H2 catalog and basically derived the internal and external pressures for about 6,000 H2 regions. Since the Muse data isn't good enough to resolve the H alpha shells, he made assumptions for 2 extreme scenarios. In one, the H2 region is basically a smooth distribution, and this gives him a lower limit. And the other one is that the H2 is coming from a very clumpy environment, and with those measurements, it gives you basically an upper limit. So internal pressure, he considered from 3 different terms. It's the thermal gas pressure from ionized gas, it's direct radiation, and the wind REM pressure. And those are all calculated together. And the external pressure is the dynamical equilibrium pressure that I already discussed before. So the first thing is basically just a sanity check. Do our measurements that you're seeing here in red, then you combine thermal and radiation pressure. Do they agree what we know from previous measurements? And reassuringly, our measurements are the same. So that means our assumptions we made are sensible. And coming now to the interesting part. So looking at the internal pressure over the external pressure, you see that a large fraction of our H2 regions are overpressurized, means they can still expand. But that there is a fraction that it seems to be under pressured, so means they cannot expand any further. And preferentially, these are located at sites where you have higher gas surface densities. That basically means in galaxy centers. So, which could give an indication that pre-supernova feedback is more efficient if you are in a disk environment rather than you are in the centers of galaxies. And basically, the last topic to cover in this is to look at molecular gas superbubbles. So these are bubbles that have sizes of about 100 to 200 parsecs in diameter. And Liz Watkins, who's leading this, has been looking through the images of all the ALMA galaxies to identify basically these bubble-like structures that you're seeing here, and also confirm that based on the gas kinematics that these are expanding shells. So if you look at these molecular bubbles and compare them to the information from H alpha as well as from HST on young stellar associations, you're getting this more complex image, but also you can start to infer the age of the bubbles, one from the expansion in the CO you're seeing, but also with the age they should have by the SED fitting of the young stellar associations. And if you compare these two ages, so with the stellar ages on the y-axis and the CO inferred cluster age on the bottom axis, you see that there is a nice correlation. There is some mismatch in the scaling, which could be of our misunderstanding on or interpretation of the cluster age or the expansion velocities. They were assumed to be basically all wind-driven. The other thing that is very interesting, because Liz was very careful to look for signs if there are strong supernova remnants or weak supernova remnants, is basically that in the one bubbles that appear to be very young, there are no supernovae, but there are already bubbles. So again, pointing to the fact that pre-supernovae expansion must happening, but also then if you go to older ages, that supernova must have play a role there. However, how much is not clear, but in these super bubbles, at least they need to play a role. So this basically brings me to the conclusion: supernova processes are becoming important in starting to disrupt the molecular gas, which potentially is quite obvious. The role of its supernovae are playing in this disruption of the molecular gas reservoir is unclear, and this might be an issue for simulations that had been, especially cosmological simulations that had been basically assume that supernova are disrupting molecular gas. So if you're interested to learn about more results, there are many more papers I couldn't unfortunately cover. There is more work ongoing. I think there will be more exciting results out in addition to the ones I discussed. If you want to go and play, learn, look at nice galaxy images, the data products from the main 3 surveys are public or almost public. All the ALMA data cubes have been released, including maps at various resolutions. HST imaging is all public, and the final set of catalogs will be released this summer at the IAU General Assembly. The MUSE data products have been all released last July, so also there's a lot of information. It's also on the stellar component that we haven't published anything or touched upon a lot. These basic data products are associated with higher level data products like CO rotation curves, cloud scale measurements. There's an atlas, as well as the software has been published also on GitHub, and everything you should be able to access via this PHANGS data page that you can hit if you get on the main page. Also, if you just want to be inspired about how diverse molecular gas distribution can look like, this is an atlas we put together for the PHANGS ALMA sample paper. And so this basically brings me to my conclusions. I hope to convince you that the cloud scale view on the star formation process can help us gain more insights on how star formation reaches. I think I want to reiterate that it's important to go down to reach the scales of star formation units to have access to new information. That ALMA combined with multi-wavelength information is very critical to also get access to the time evolution of the star formation process, which is very fast. The molecular gas is close to energy equipartition, and it seems like that local properties seem to matter more in setting the exact conditions than global ones. The star formation itself is clumpy and inefficient, but once it starts, it proceeds fast. And pre-supernova feedback and supernova feedback are important. However, the relative role, I think, is unclear at this point in time. Thank you.
Thank you so much, Eva, for this wonderful presentation with so much data. I mean, it's overwhelming. And so many results already extracted from this data. So thank you so much. I'm sure there's a lot of questions in the audience, and Françoise is there. And then we go to the Zoom to see if people have also questions. So please raise your hands for those who are following this from afar.
Thank you, Eva. It was so rich and so full of data that I don't know how to begin with. Maybe I was more interested in this violin diagram we show with bars, in fact. So you show that the efficiency, or the depletion time or efficiency of star formation was varying a lot in both galaxies, but not in, yes, this one. Yeah. And have you detailed that in function of strength of the bar, length of the bar? Is it nuclear bar, primary bars, or all these?
So in the paper, Miguel looked in that. Of course, was one of the first questions also Sharon might ask. There were no obvious trends. I think the sample is 40 galaxies, and potentially this might still not be enough to do that. The thing we haven't done at that time, I mean, we now have classified the gas morphology, also looking at the gas along the bar lanes more, but we haven't done this with that. I think the problem is, and you know that much more than anybody else here, is that you also have the time evolution of the gas reservoir imposed by the bar, and we suspect that that might also play a role with what we are seeing, but the data wasn't. Yeah, we didn't push that in that paper because it was beyond the scope, and this would require a lot of more other assumptions. Yeah, but it's surprising, and I've been just looking at lower resolution data in the centers of BART versus on. It seems to be something that is significant. So it's not that bars always drive a lot of star formation in the centers, and I was kind of a bit surprised, but it makes sense.
Yes, yes. And a related question is, have you looked at the influence of the velocity dispersion as a function of radius of the gas? Is it less efficient when it is hotter, or you know what I mean?
So with the velocity dispersion, one aspect we are still worrying about is that we might still have a contribution from the stellar, from the gravitational potential in the centers. They are in this rising part of the rotation curve. This attempt has been made basically in, I think, in Jai's big paper. And I must admit, I lacked the time to fully read it in here. I mean, all these measurements are accompanied in tables, and once the paper is published, all these table and information will come out, so people can also go and look.
I will look on this paper.
Any other question?
Thank you. Maybe I have a naive question about the way you measure star formation efficiency. Because you measure the star formation rate on one hand, fine, and you measure the gas density, but that's the remaining gas. It's not the gas which was used to form the stars. So how does the total mass of stars form, the total mass, not the rate, compare to the remaining mass of the gas? Is it negligible? Is it a large fraction? When you see galaxies where you have only star formation rate and no gas, it may simply mean the gas has been exhausted by the star formation.
Yeah, so I think this is a different use of the same terms in different communities. So in extragalactic studies, traditionally, people have talked about star formation efficiency using the ratio of molecular gas mass to star formation rate, as you say. Whereas in galactic studies, people have indeed taken into account the new amount of stars that have been formed. This is much harder at in external galaxies, where you have no measure of the low mass young stars that are formed and how to do that, and therefore people have not done it. I think on large scales, extragalactically, people have started to look into calling this ratio, or the inverse of the ratio, calling it the depletion time, which potentially makes more sense. I think it'll be hard to get a good measure of the number of young stars formed to do the exact calculations, because assessing the young low mass stars, how much they are formed is different. And I think you need to make assumptions about the IMF. And if the galactic or people who are doing this at high resolution can tell us it's universal, this will be easy. If the debate, if there's a more top-heavy IMF in the most massive star formation regions, then this will be harder.
Thank you for a very interesting talk. I have a question about when you talked about the environment, when you studied the effect of the environment on the star formation. Do you in some way consider the effect of dark matter halo? For instance, if the galaxy is in a cluster or in a more denser region, or for instance, the halo, estimating the properties of the dark matter halo, how it can affect the star formation?
No, we didn't do that, but yeah. So for our study, we didn't do it. We basically did a distance cut. We have a couple of galaxies that are residing in the Virgo cluster, and also one or so in the PHANGS cluster, but we didn't do that. Also, the area we are covering is basically where you have the most of the star formation. So that means we are pretty much in an area where dark matter within a galactic halo shouldn't matter. There's the Virgo survey. They are doing the observations at a few hundred parsec resolution, lower resolution than we do. And I think those are results that are coming out. So I'm just showing here the nice image from Toby Brown's work. And of course, the one next obvious step would potentially be, if we go to cloud scales in Virgo clusters and compare those properties to the ones we see in the field galaxies, do we see differences? So this cluster environment, how does that impact? So that clearly is one obvious next study to do.
Okay. Thank you.
Is there any other question in the room?
Thank you for this wonderful talk. There was really much information, but I have one question which might be a bit naive, and it's on the scale of Muse observation you showed. I think it was at the very end. So with Muse, you were not able to resolve H2 shells. And after that, you talked about superbubbles. And was it, I didn't really understand it at this point. Were you able to understand or to measure the exhaustion of the superbubble? Yes, exactly this. So the H-alpha, I'm not sure if I really understand what I'm seeing here. The bright spots here, are these H-alpha emissions?
So the H-alpha emission is basically the pink thing. So the nice, to calibrate your eye, if you take the bottom right, the second image, was really pinkish. That is the H-alpha emission coming from Muse there. So all these features were hand-selected, and they are super bubbles. So that means they have really large values. And these are 31 bubbles across the full sample of, I think, 70 galaxies or more that have sufficient ones. So these are very specific and special regions. So the idea is that potentially you don't have not only one stellar cluster, maybe you have two or short generations of star formation in the clusters with huge energy. So these should be the regions in the galaxies where you have the most massive star formation across. So these are special regions. Yeah. So that you also can eject a lot of energy to have a significant impact on the molecular gas at our resolution, which is around, I think, also probably here about 100 parts and better. So this was basically using the best available CO imaging for each galaxy, which ranges from 50 parsecs to 150 across our full sample, just how Alma observed it. And so here then, I think they have not started for this work to look also into a couple of galaxies have H-alpha imaging from the HST. And there you see smaller H2 regions, and these are the more typical ones, which I alluded to in the previous study. So whatever shows up here would not have made it into the first study, in the previous study, because it's unclear to see how the H-alpha emission hangs together. So the idea there, the requirement was these are compact H2 regions still where you can say they're coming from one single source. There's here you're one step further and on larger radii.
So I don't really have a feeling on the radii and on the scale. So are these moreover birthplaces of huge clusters, of huge star clusters?
So the scale bar, the white one you see everywhere, is 150
Okay.
parsecs.
Okay.
So that should give you an indication. The radius is the bubble radius, so that's the circle, and that's always the same. So you see that the radius is 150 parsec in the bottom and goes up to much larger structures of, if you go, for example, in the left-hand side of the plot. So,
okay.
and yes, unfortunately, in 3D, these bubbles in molecular gas look more convincing than you try to show them in 2D. So,
okay. Thank you.
The other question? In fact, I had one myself. I was stunned about your conclusion regarding supernova, and the role of supernova and the feedback. And so what is your, guesstimate about how to go forward?
One way to go forward is basically improve on this study. And Ashley Barnes had followed up this work by using the spatial information from HST, H-alpha imaging. So to basically have not to make the assumptions, but rather have a true scale measurement. And has demonstrated that once you do that, these two areas become smaller. So you can get a handle on the effect of pre-supernova feedback in combining views with HST imaging. So that would be one way. Then you have larger samples. I think generally the way forward, I would say, is larger samples covering more environments. So far, people have done those studies in the Milky Way, but there you have the problem of the distance. However, there the Sloan 5 local volume mapper probably will teach us a lot of more information. And also for the Magellanic Clouds. And then there are a few nearby but low mass galaxies where people have tried these studies. So now pushing that to more massive galaxies also that have much higher gas content will be important to our abilities. I think to some degree, it's interesting that we haven't utilized all the information that's available in the local galaxies because we are lacking the high quality data. And I think what becoming clear with PHANGS, getting such a data set is as expensive as doing a deep field. And that is not always easy to convince the tech that you really need to spend so much time to gain information.
I had another question is, clearly you have a embarrassment of richness in terms of data and information. So my question is, what will the JWST bring you in terms of new aspects? What do you hope to see?
Okay.
What you're going to see?
Let's see. So why do I only put this in? Because it's a nice picture. So what you're seeing here is basically HST in the background. And in green, you see molecular gas emission at about a factor of 2 to 3, lower resolution. I think HST will tell us if all these dark regions are indeed hosting embedded star formation. I think that's one big question. Do we miss star formation? Do we miss the early phase of star formation? And where does it occur? Is it basically the same with the ones we already see in H-alpha and the young clusters? And this gives us a much better handle on the time evolution, how fast it proceeds. And the other thing JWST will bring us is also a lot of information about the PAR emission and how PARs live and are destroyed near star formation. I think this is a totally new aspect. Hot dust grains, how those are heated. And then on the stellar cluster side, the important aspect is you're getting much more better and precise ages and therefore masses, and you can break the extinction attenuation, the attenuation, age degeneracy or metallicity. And I think we are starting to see that also metallicity, even for older populations, that the assumptions that were made to fit these single stellar populations are too simple, and metallicity plays a role. So I think there's people who love clusters will learn a lot, even if they don't care about young clusters, but older ones, there's a lot of them. And also then, yes, I mean, our main motivation was to go after the embedded star formation phase.
So I don't know if there's any more questions here, but maybe on the virtual world of the Zoom. Do this. Anybody raising? Is anybody in the Zoom? I mean, can you raise your hand if you have a question? Or? Apparently, they're either overwhelmed or it's so clear that they don't have any question.
Or they're reading papers.
Yeah, exactly. Good. There seems to be no. Elaine, you have a question, or apparently nobody. No, there's nobody. Okay. No. Good, then I think that was it. So once again, many thanks for this very nice talk, very rich, and again. And thanks for you being here and in real, and thanks for everybody who has been there and virtually. And so thank you again.